Saeed, please, the stage is yours.
Sure.
And looking forward to your presentation on new advancements in deep learning to improve visual inspection.
Thank you so much for the introduction. Looks like we have our exclusive Canadian session today because I'm also based off Canada. I work in our R&D center of Musashi AI in Waterloo. So, is moving also? Is this? OK. So Musashi AI was founded in 2019. Our parent company is Musashi AI Japan. It's just a joint venture with Musashi, Sumitsu, and 6AI. Musashi AI is specialized in gear inspection, shaft inspection, and we also have our own Syndian software platform. Musashi has found that inspection and transfer of the parts each of them is 20% of the workload in the factory environment, and automation of them will help transition the workforce to more value-added tasks because the repetitive task of inspection is prone to errors over time, especially when the inspector is tired. And our 634 AI is sister company is focused on indoor mobility. So Musashi has been manufacturing automotive parts for Musashi Sumitsu has been manufacturing automotive parts for the past 8 years, and before Musashi AI was founded, Musashi has experimented with a lot of off-the-shelf solution for rule-based machine vision systems, but most of them had failed because of the fact that the parts we have are complex parts because they require full 360 inspection, and which means that the robot has to move around the part. The parts are not clean. They have a variety of geometries along the part. The list of defects is long, so it's not only limited to porosities. We have to do measurement on the part, and customers usually have their specific requirements in terms of checking the presence of the certain elements and proper installation of them. So that makes it very challenging for typical deep learning or rule-based machine vision algorithm to properly address all of these items. You might ask why we need anomaly detection in machine vision, especially with the advent of deep learning algorithms. There's success with supervised methods because we can train them on a data set, and that data set would suffice if we have similar defects to that data set. But when it comes to real industrial scenarios, there are 3 things that prevent further successful supervised methods. One is the lack of defect data. That defect data might not happen in a short frame of time. Second reason is the labor-intensive task of doing annotation. So annotating, especially segmentation, is very time-consuming. And the third reason is that we sometimes don't even know what type of defects or anomalies is going to happen on the line. So that's the third reason that anomaly detection is required to catch the data. And it comes with the added bonus of passing all the good parts and classifying defects. If we know the label for the defects, some anomaly detection algorithms can label them, and they can also catch the anomalies or unknown types of defects. And we can start the inspection quicker because we can train the algorithm on only good parts. So anomaly detection can find the deviation from normalcy and expected and outliers in the data set. Broadly speaking, we have 2 types of anomaly detection algorithms. One is generative methods, where the goal is to construct a model of what is normal, and whatever falls outside of normal data is called abnormal. So these algorithms have their own benefits, but they have the big drawback that they barely can tolerate deviation from the normal data. So if you have a rare occurring normal deviation, that will cause a false positive for these algorithms. Second type are discriminative algorithms, where we can separate good from bad anomalies. So that in that sense, it's not dealing with the issue I mentioned for generative methods. But it also comes with the extra requirement for having NG parts included in the training set. So that's that was a quick overview on anomaly detection algorithms. But typical anomaly detection algorithm will have challenges on complex parts. And some of these challenges are listed in this slide. So for instance, if you are, sorry, how can I go back? So if you're looking at this particular image, there is an anomaly here, but because this has a very low contrast, and it's highlighted here, that anomaly, typical anomaly detection algorithm might fail to detect that. Also, the anomalies that we have on our complex parts are very small. Sometimes they are less than 1% of the pixels in the image. And that's another thing that is vastly different from off-the-shelf anomaly detection algorithms that are out there. And the third thing is texture variations, because there's parts that their texture changes a lot from one day to other, and that might throw off the anomaly detection algorithm and cause false positives. So as you can see, the texture changes here, and it could cause a false positive or anomaly detection if it's not designed or built for complex parts. So these are the motivations that we had when we started building our own proprietary anomaly detection algorithm. And I'm going to explain a little bit more about some of the fundamentals of data labeling in supervised and unsupervised and semi-supervised deep learning methods. So if you imagine if we had a network that can extract the features for images, these dots are representative of those images in a 2D space, which is a very condensed representation of the data. So if we have cracked data, these dots would possibly belong to that class if the feature mapping is reliable. And if we have dent data, these dots would possibly relate to that dent data. So each of these dots are a representative of an image. And the prosody, same thing for the third class. So typical unsupervised method would not require human annotation. So what it does, it works based on the similarity of the points. And based on the similarity of the points, it will group them together. So we could draw the lines between them. Another type of data annotation method is supervised, where human expert labels all the data and models trained to put them in a group together based on the annotation that is received during training. So it's very strict in terms of whatever falls outside of that defined boundary that happens during the training would not be classified as crack or prosody or dent. And there is a hybrid approach where it's more relaxed in the rules. So we can, and it requires less time in terms of annotation, and it's more forgiving if the sample doesn't necessarily fall inside, but close enough to the boundaries of decision. So with that, let's move on to our workflow for anomaly detection, where we train a generative network to accept an inspection image. What this network does, it will remove the noise or anomalies from the original image. So what you have here is an image without anomaly. So that's a big step toward finding anomalies, because we can do some sort of image subtraction to find an anomaly map. And that anomaly map will be sent to shape analysis and binarization, where the processed anomaly map and secondary threshold are the results. What happens here, we check the size And if certain elements are smaller than the specifications, they will be eliminated. And with the aggregate thresholding algorithm that is special in our anomaly detection, we'll be able to find accurate boundaries of anomaly. And that allows us for the segmentation when it comes to measurements of the anomalies on the image. The result from this part would be sent to region cropping. So if we find that this is a potential anomaly, it will be sent to region cropping. I'm going to explain further about region cropping in the future slides. But what is the output of region cropping is a smaller image that is cut from the large image. And that small image is being sent to a type of classifier called pseudo one-class classifier. And that's a critical component of our algorithm, where that classifier decides whether that anomaly is a normal variation or a well-defined defect class, or is a novel imperfection that hasn't been seen before. So we talked about supervised, unsupervised, generative, and discriminative. That model over there is an unsupervised and generative algorithm. If we go back to the definitions I provided earlier, and this model here is a semi-supervised and discriminative algorithm. So we are taking advantage of both of the definitions we had earlier. So that's a big differentiator factor for us when it comes to comparing our methodology to other anomaly detection software out there. So going back to pseudo one-class classifier that I showed in the previous slide, I'm going to provide more details on how it works and why is it special. So if you imagine that we map the samples for feature space, similar to the dummy example I provided earlier, the OK class is indicated by green, red class, NG class is indicated by red, and the x-axis is the confidence. So a typical binary classifier would allocate or assign the high confidence samples to the related class. So an OK class will include the data inside of the green circle, and bad class will include the data on the red circle. And the question remains, what happens to the entries in the middle, which have low confidence? That's where our method comes into play, where it classifies and assigns the label of novel anomaly to them. And this is something that we have developed in-house, and it's patent pending. So we have now the three things that we wanted to differentiate: OK variations, well-known defects, and novel imperfections. So region cropping works by taking a binary anomaly mask after binarization and tries to work with the boundaries of these masks. In order to process the anomalies and send it to classification network, we somehow have to fit them into the fixed input size for the classifier. Two traditional methods for that were either crop a fixed window size around the anomaly, or crop a small confined box around the anomaly and then resize that to fit box A. So option A and option B, where we crop it and then resize the image. Both of them have their own drawbacks. First one includes too much context for small anomalies. It might be misleading for the classification network. We'll have degradation when it comes to classification. And the second one, we are basically changing the aspect ratio and appearance of the anomaly. So that's not a good thing when it comes to classification accuracy. Here are some results of why these two methods fail. First one, we have multiple anomalies in the same image. Not good for when it comes to classification. And for option B, this was a rectangular anomaly, but it has been stretched to look like a square. And we have lost a lot of information in that transformation. Second one, this looks like a dot, but since we don't know what is beyond these pixels, that might mislead the network to misclassify it. So our algorithm decides what is the proper size, and the 0 pads the rest of the image, so it becomes hidden. The results from our algorithm, where the anomaly has maintained its aspect ratio and shape. Also, it contains enough context around the background, around the anomaly to make a proper decision. Some results that I would like to share with you about with regards to our anomaly detection. This is a very rare type of anomaly that has been caught in the first time that the algorithm sees it. And the second one is an unusual shape anomaly that anomaly detection has been able to segment it out from the image. So we have successfully implemented inspection solutions for manufacturing of automotive parts with high standards. And we are confident that these solutions will be very helpful for other industries with similar challenges. A quick summary of what I discussed in this presentation. We have introduced a true anomaly detector using a typical binary classifier. We have reliable detection of well-known defects, which is very valuable in terms of labeling anomalies. And that became feasible by having sufficient background context for the cropped image and also maintaining the aspect ratio and size of the anomalies. And going back to the big picture, this yields a very highly accurate overall implementation. And we have also the feedback loop where we can feed the anomalies found to our supervised algorithms, which I didn't get to talk about today, but we have them in our platform because we are leveraging unsupervised and semi-supervised methods, and we also have generative and discriminative in the pipeline. We have a dynamic region of interest where we can define where to look at in the image, so the irrelevant areas will be ignored by the algorithm. And this comes with the measurement capabilities, and it runs on embedded devices. So it means that we have to, these algorithms are very, very fast. So at the core, we are a software company, but we provide optics and robotics, electrical design consultation. And we also provide sentient analytics platform for the customers to follow the trends on their manufacturing lines and have a better high-level understanding of what are the root causes for those defects. Please feel free to download our app on your iPhones and iPads and see the power of AI in your hands. You can do a different object detection models, and we would like to invite you to our booth at this show, and we'd be glad to talk further about our developments and our solutions. And thank you so much for listening.
Thank you, Saeed, from Musashi AI. Sorry, no time for questions.
Okay.
But visit him at the booth later on tomorrow. So thank you.
You're welcome.